Welcome to reactions of substituted um, benzene. So aromatic substitution. So we're doing electrophilic, aromatic substitution. So that's the reaction mechanism. And this particular section we want to talk about substituted benzene. So we want to do the same reactions that we did in the previous lecture, but now we're doing substituted benzene. So before, benzene was the starting material. Now what if we had toluene? So if we had toluene and we do nitration, so if you want to do nitration of toluene, what's our reagents? Nitric acid and sulfuric acid, and that makes your strong electrophile NO2 positive, the nitronium ion. And so how does this react differently than benzene? Well, toluene is 25 times faster than benzene. And so we would call the methyl group, the CH3, an activator. And you'll see here, you can get the nitro group here. You can get the nitro group on this carbon, and you can get the nitro group on this carbon. Now, if you put the nitro group on this carbon, that's the same thing as this one. And if you put the nitro group on this carbon, that's the same thing as this one. So one of the things you need to be able to do is see that this is a 1,2 substitution. So if your methyl is a 1, the nitro is a 2, we also call that ortho. So this would be ortho nitrobenzene. And sometimes you just write O, nitrobenzene. Okay, this next one here, that's a 1, 2, 3. So this is a 1,3 substitution, and that's called meta. So that's meta nitrobenzene, or you could just write M, nitrobenzene. And then this one here, 1, 2, 3, 4, that's a 1,4, and this is called para nitrobenzene, or P nitrobenzene. So one of the things you need to be able to do is name that. Now I'm going to give you the percentages of how much these were made. So this one, the ortho nitrobenzene. So one of the things you need to be able to do is name these ortho, meta, and para. But the other thing is they're not all equal. So the ortho for nitration of toluene is 60% yield. The meta is only 4%, and the para is 36%. So you get a mixture of ortho and para. And so what I will ask you to do is, I always ask, what is the major organic product for this reaction? And what you would want to do is you would want to draw the ortho and the para. Okay, so you would want, and you could just pick one. You could pick ortho or para, or you could do ortho and para. So why do we get one over the other? So let's look at this mechanism. So if you have toluene and you have nitric acid and sulfuric acid, you get your nitronium, and you know that you're going to make the sigma complex. So let's just go ahead and choose the ortho. So let's do ortho. We're going to do our sigma complex. So if we do this ortho, we put the NO2 here, and we put our sigma complex there. Now let's do our resonance structures. So these electrons go here. Now we have our sigma complex there. And we can do this again. Now, is that the only resonance structures? Well, let's look at nitro. So nitro and the methyl. So if we have this, all right. So there's your nitro and there's your methyl. And so this is your sigma complex, and then the next thing that would happen is you can do your HSO4 minus, and it would come and take the hydrogen here, and that hydrogen would re-aromatize after abstraction, and this shows you the ortho nitro benzene. Okay, so that is our mechanism. So let's just look at an energy diagram for the nitration of benzene. Okay, so why faster? That's kind of what you're going to be looking at. So you're going to learn the directing groups. So why is it faster? Why is toluene 25 times faster than benzene? That's what we're going to talk about. Okay, and then so that's one question you need to be able to answer this. And then two, why is your major product, organic product, ortho? We call it ortho para. And so that's what we're going to do during our POGL. And I want to show you an energy diagram, because when you ask why is faster, you've got to look at the height of your activation energy. So I just want you to see that if you did a reaction coordinate, reaction energy diagram, you would have benzene. So if benzene and toluene are equal here, so they're equal energy, and then let's say benzene goes here, and this is your sigma complex. And then you could see that here you have meta. So meta is still faster. So this is CH3. There's your nitro. There's meta. Toluene. And then here, even lower, you have orthopara. So we'll just do like that. Okay, so this is ortho or para. And so you see that the height of your activation energy is lower for toluene. Here, this one's benzene. And then you have these graphs in your slides. And so that is a picture showing you that experimentally, toluene is 25 times faster than benzene. And your major products are going to be orthopara because the transition state activation energy is less than it is for benzene. So what I want you to be able to do is understand why, and then I want you to be able to do these reactions with all kinds of different directing groups. Let's do your POGL activity 20B. So Model 1 talks about the rate of substituted benzenes. EDG. And then we have EWG. So what is EDG? This is electron donating group. And EWG is electron withdrawing group. So 1A. Based on the information shown in Model 1, an electron donating group, did you circle donates? Electrons to form electrons 2. So it's going to donate electrons 2. So you could put a lone pair here, and those electrons are going to be donated to the benzene ring. Draw an arrow to show. So that's what we just did. The polarity of the bond between the benzene ring and the electron donating group. So just show the electrons are being donated. Electron donating group makes the aromatic ring more nucleophilic. Okay? Because it's donating electrons into the ring, it's more electronucleophilic. And that's why you have a faster reaction. That's why toluene is 25 times faster than benzene. 1B. An electron withdrawing group will withdraw electrons from benzene. Draw an arrow showing. So there you go. It's pulling the electrons away. The electron withdrawing group makes the aromatic ring less reactive as a nucleophile. Okay, so this one's going to be slower than benzene. So benzene's kind of the standard, and then you compare the rate. 1C. An aromatic compound that is more reactive than benzene is called an activator. Which group would make an activator? And that would be an electron donating group. An aromatic compound that is less reactive is called a deactivator. And those groups would be an electron withdrawing group. In your groups, discuss what functional groups would be classified as electron donating group. List at least 2 groups from these classes. You have a very awesome slide in your slide deck that show this, and I'm looking for it right now. Let's see. Right here. Okay, so I will copy it here. So here you have activating, make that green, activating. Okay, and activating are always going to be ortho pair directors. So they're going to be faster than benzene. The rate of reaction, they're going to react faster because they're more nucleophilic. And they're going to give you the ortho pair product. And then you have this, which is deactivating. And these are going to be meta director over here. Now there is some exception here. And this is deactivator. So that means they're slower than benzene. But these are going to be ortho pair director. And that's your halogens. So that's a fluorine, a chlorine, a bromine, and an iodide. Now the ones that are activating over here, you have pi donors. So that means they have a lone pair that are going to donate into the pi group. You have anilines, you have phenol, you have an ether, and you have an amide. Those are pi donors. You also have sigma donors. And sigma donors, what we saw with toluene. So R is like any kind of alkyl group, toluene, those are alkyls, and then also aromatic. So a pi, those are aryls. Okay, so those are sigma donors, and they are electron donating groups. And then you have here deactivating. So these are going to be slower than benzene. They're going to react slower, and they're also going to give you a meta product. And these are like your carbonyls, and that, so you have a ketone, a carboxylic acid, an ester, and what these have is these have this delta positive carbonyl. So that carbon that's bonded to that ring gives you a slightly delta positive. Same thing with sulfonic acid, nitrile, nitro, and NR3 positive. So anytime you got that positive atom connected to the ring, you're going to get a meta director. Okay, so those are the groups for electron donating and electron withdrawing groups. And that slide is really great. It's slide number 47 in your chapter 17 slides. Now, it says here, drawing resonance structures can predict whether a group is electron donating or electron withdrawing. Using curved arrows, draw 3 resonance forms of the anisole. Okay, so you will have to do this if I ask for a mechanism and ask for all the resonance structures, and this explains why. So I just gave you the pattern, but this is going to explain why. So if you draw this here, you can see that those pi electrons are donating inside the benzene ring. And so these electrons then can go here. And you see how you get a negative charge on the ortho position? So this is ortho, right? And this is para. There's your para. I did it wrong. Your electrons, you always start with your electrons. The negative charge goes there. and you redraw. So now we have a negative charge there and there, and you can see that that is ortho once again. So you get more of a negative charge on the ortho para position. So that's your nucleophile. And you're going to be attacking a strong electrophile. So the oxygen donates the electrons from into the aromatic ring. This is anisole, by the way. Anisole would be a activator. And you see anisoles right here, right there, OR. Because it donates the electrons and it makes it more nucleophilic than benzene. Using curved arrows, draw 3 resonance forms of nitrobenzene. Okay, so now let's do nitrobenzene. And a nitro is a deactivator. So when we draw our nitrobenzene, nitro is a deactivator. And you should be able to see that because you can see your nitrogen that is directly attached to this ring has a positive charge and a formal charge, even though this is overall neutral. So if you draw this, you would see that it withdraws. It withdraws. So here, those electrons go here, those electrons go there. And then you get a positive charge, not a negative charge, a positive charge on the ortho. So this is not a nucleophile. So you do not want to attract a electrophile at the ortho position. Then those electrons would get pulled here. And once again, you get a positive charge on the para position. So you would not want to attract an electrophile there. So this is why these are deactivators. They're making the ring less nucleophilic, and you're actually getting on these resonance structures positive charges on your ortho para positions. And this is why you don't get the electrophile adding to these positions. And so once again, this is the ortho position. So 4B, the nitro group withdraws electrons from the aromatic ring. So you see how it's pulling those electrons here? See in that first one, it's pulling those electrons. Nitrobenzene would be a deactivator. Explain. The nitro group withdraws electrons from the aromatic ring, so therefore it makes it more positive. It's not nucleophilic. This slows the reaction rate. But also you can see why you also get, this is a meta director. So if you do get an electrophile added to the benzene by electrophilic aromatic substitution, it's going to add to the meta position because the meta position does not have a positive charge. Let's go on to Model 2. Model 2 is about the directive effects of methylbenzene. And we know methylbenzene is toluene. Nobody calls it methylbenzene. So here we're doing nitration. Here's reaction 1. This is reaction 2. So question number 5. Alkyl groups are slightly electron donating. This is an alkyl group, slightly electron donating. So it's electron donating group, so it would be an activator. In the nitration of toluene, what product is formed in reaction 1? So we've added the nitro to the ortho position. In reaction 2, we've added the nitro to the meta position. Draw curved arrows in both reaction 1 and 2 to show electron movement. So here we have these electrons that went here. And there's your nitro. And then here we do the same thing, except this time the nitro added to this carbon. Draw any additional resonance forms for cationic intermediate. So the sigma complex formed in the reactions above. So at reaction 1, we want to show resonance. So this is reaction 1. And the electrons always go to the cation. So this is your sigma complex. And then we redraw this. Now we have the positive here. And then we redraw. And we have this. Okay, and then reaction 2. We're drawing the resonance structures for reaction 2 if we had a sigma complex. So we start here. And those electrons, then we go here. Now, we drew all of the resonance structures that are associated with reaction 1 and 2. Circle any forms that would be a major resonance contributor in reaction 1. So if we look at reaction 1, we have a secondary, kind of secondary allylic carbocation. Here we have a secondary allylic carbocation. Here we have a tertiary allylic carbocation. Okay, so that's going to be more stable. That's going to be particularly more stable. Here below we have a secondary allylic, here secondary allylic, here secondary allylic. So nothing more stable than what you would see in benzene. But because we have this methyl group here, the substituent, we get a tertiary allylic carbocation, and you know that that is going to be more stable. So question D, of the two products in Model 1, one product forms and the other does not. Circle the product that forms and explain your reasoning. So it is the ortho product that forms, and it's because of this tertiary allylic carbocation. 8. Draw the three resonance forms of the cationic intermediate, the sigma complex, that forms when nitronium adds to the pair position. Let's do number 8. And now we're adding to the pair position. So when this product is formed, what do those resonance structures look like? Okay, so we're taking this here. Well, it won't be that one. It'll be this one here. This is your pair position. We'll put in our hydrogens. Those electrons will go here. Now we draw PH3. And now we have to go to the pair position. So let's add the nitro here. And then this gets our positive, that carbon there. Now those electrons go here. Resonance structure. These stay the same. Nitro, we still have a hydrogen here. We have a hydrogen here. And now we have the carbocation there. That carbon. And then those electrons, we just did those electrons. So now we're going to do these electrons. And then you can pick any particular sigma complex to do your reatomization. I'll pick this one here, do reatomization, and I'm going to erase these electron flow arrows so I can show my story, and my story would be HSO4 minus would come and take this hydrogen, and that's how you would get the product there. So there's your sigma complex. Now, the para-cationic, let's just call the para-sigma complex, is very close in potential energy to the ortho intermediate in reaction 1. In what way do these two sets of resonance structures similar? What is similar is this structure right here. And you see that that is a the sigma complex here has a tertiary allylic carbocation. Now for C, the energy diagram below shows the addition of an electrophile to a substituted benzene to form ortho, meta, or para. Label the corresponding line of the energy for ortho, meta, para. So here we have energy, we have reaction progress, we have our R group, which is toluene, and it's just showing you these three lines here, and they want you to label. Okay, so the first one has the highest activation energy, and this is meta. The second one would be ortho, and then the third one, if para is the most, would be para, because it has the lowest activation energy. Which products would you expect to be favored? So ortho-para. Would all activators to direct the same position? Yes, so all activators will give you ortho-para. Model 3. This is called General Directive Effects. And we have two reactions. And this has an electron donating group, EDG. We react this with an electrophile. And electron donating group. And we see that the electrophile adds here. And it adds here. This is reaction 3. And then we have another reaction where we have an electron withdrawing group. And when we add our electrophile, our strong electrophile, we see that this group adds in this position. And this is reaction 4. So now let's look at our problems. 9a. In reaction 3, what products are formed with electron donating groups? Did you write ortho and para? 9b. In reaction 4, what product is formed with electron withdrawing groups? This is meta. So meta is the 1, 3, 1, 2, 3. And orthopara is orthos 1, 2. This is ortho. And then this is 1, 4. This is para. What groups, electron donating group or electron withdrawing group, would be orthopara directors? Did you circle electron donating groups? What groups would be meta directors? Electron withdrawing groups. So these are meta directors and these are orthopara directors. Number 10. Consider the reaction of anisole with an electrophile. All right, so let's draw anisole with an electrophile. Anisole would be well, when you have the lone pairs there, that's going to be an activator because those electrons can go into the benzene ring and make it more nucleophilic because of the lone pair. So activator. Draw the 3 additional resonance forms for the cationic intermediate, the sigma complex, when the ortho product is formed. All right, so we are going to put our hydrogen here, our hydrogen there, and we will have this electron going here, and then we draw our sigma complex. And we have our electrophile here at the ortho position, and then we get the sigma complex there, which is a little different than where they placed it, but it's going to work out to be the same. Okay, so your resonance structures could be this. Those electrons go there. And then you get the sigma complex there. These electrons could go here. goes there, and then you get your positive there. Now you get another resonance structure here. These electrons can go there. And this is very important. This is why it's an activator and a orthopara director. Okay, so repeat the above process for the sigma complex formed as a result of a meta addition. So these things take a long time because we're drawing all of the resonance structures, but it's a good exercise for you. So what if we put this in the meta? So we have the electrophile, and what if we had this here? So if this went meta, and there's the 1, 3, so that's your meta. And then you get your sigma complex here, and those electrons go here. So let's draw our resonance structures. We have our sigma complex there. And we have this one. Now, do you see that the lone pair on the oxygen was never able to donate its electrons into the ring when it was meta? So if you have your substituent on the meta, you have these resonance structures, and here you have the positive cation here and here, so you never have it on this carbon. And it's that carbon here that right here, so when it's there, those electrons here can push towards that carbon, and now you can get your positive charge on the oxygen. This is so stabilizing, and I think if you look it up, you'll see that this is like, I think 10,000 times faster than benzene. So we talked about toluene being 25 times faster than benzene, but I think this reacts 10,000 times faster than benzene, and it's because of this resonance structure right here when you put on an ortho, and you would also get that if you had a para. So let's see what the question is. For 10D, what is the main difference between the resonance forms drawn for the ortho product compared to the resonance drawn for the meta product? Okay, so we just circled that one where the positive charge is on the oxygen. Would you expect there to be any difference in energy between the sigma complex and the ortho product and the sigma complex and the meta product? And you would say yes. This intermediate, so this would be an intermediate, would have a much lower energy than the other one. So if this is the ortho and this is meta, this would have a lower energy, and therefore it'd have a smaller activation energy. Okay, for F, would you expect there to be a major difference in energy between the sigma complex for the ortho complex as compared to the para? And no, there wouldn't be. So you can go through this exercise here, and you can then put your electrophile on the para. So if you do this exercise, you can go through this exercise, and then you can put the electrophile at the para position and draw your resonance structures. And I will let you do that. So now if you put the electrophile in the para position, these electrons go here. And you have this, and this starts your resonance structures. Here's your electrophile. And now you have your positives there. And the nice thing is here, those electrons can go there onto the ring, and then you get the resonance structure with the positive charge on the oxygen. And you could draw another resonance structure, but it's this one here. Usually an activator is an ortho or para director, and a deactivator is a meta director. However, a halogenated benzene is a deactivator. So if you have benzene, bromobenzene, this is a deactivator, but yet it has lone pairs. Okay, so this is the exception. Draw bromobenzene. So it's a deactivator, which means it's going to react slower than benzene. But it's also, it's an odd one because it's an ortho para director. And you remember that the meta directors are the deactivators. So this is the exception. So place a polarity arrow on the carbon-bromine bond. So between this carbon and bromine is your polarity. That's the direction of electron flow. So it's pulling the electrons out of the ring. So this is going to be slower. It's going to be less nucleophilic than benzene. But using this information to determine what effect induction would have on the rate of bromobenzene in a electrophilic aromatic substitution. So it would decrease the rate. So this is going to decrease the rate. Inductive effect is the polarity through the sigma bond. That's what inductive means. Okay, so let's go to the next question. Draw the sigma complex formed on reaction of bromobenzene with electrophile. So now, since I already know that bromobenzene is a ortho para director, I'll just go ahead and put it on the para, the sigma complex. So we have this, and have this hydrogen, and we have this electrophile. And now we have the positive here. And we have these electrons on bromine that can go into the ring. And bromine has an expanded octet, and it can also hold that charge. And so this is the reason why that electrophile can go ortho or para, because then you can get that positive charge on the bromine. Consider the reaction of nitrobenzene with an electrophile. So nitrobenzene, let's draw nitro out. So remember, I say that you can solve most all problems through a correct resonance structure. Okay, so if you add the electrophile here, we know that nitro with the positive charge there is going to pull electrons from the ring, so this is a deactivator, and all deactivators except for the halogens are meta directors. Draw the additional resonance form for the sigma complex for the ortho product and the meta product. Okay, so we're going to draw the ortho product, and we're going to see why it's a meta. So here, we put the electrophile here, then we get a positive charge here at the meta position. Those electrons go here, so let's draw our resonance structures. We have our plus charge there for a sigma complex. Those electrons go here. This is going to be the important one here to explain why. Look at this. So here we have the positive and positive. These will repel each other. Okay, so, and if you did having two positives there will repel each other. If you did the para, so we just did the ortho, if you did the para, you're going to get this same intermediate, and this is not energetically favorable. And so if you do the meta, and you do those resonance structures, you'll see that you never get this positive-positive interaction. So it's particularly unstable. In your groups, discuss any differences in energy between the sigma complexes for ortho and meta. Explain how these differences lead to a preference for the meta product. And that's what we just said. So if you do the meta, so let's do the meta just to show the difference here. So if you add your electrophile to the meta, so we're going to add it here. So we do the 1, 3. And we're going to add it on the meta position. There's our electrophile. We still have a hydrogen here. We have a hydrogen there. And now we have the plus sigma complex there. Okay, so these electrons here can go there. We can draw a resonance structure. Draw our sigma bonds. And now our plus charge goes here. And then we can draw another one here. And as you can see, you never have any of the positive interactions on the meta. So that is why it is a meta director. All of your meta directors have a positive or a delta positive carbon attached to the ring, and you really want to avoid this positive repulsion. Let's go on to Model 4. Model 4 talks about steric effects. Ortho versus para. So we have sulfuric acid and nitric acid. So this is our sulfonation reaction, right? So what is our, oh, actually, no, that's nitration, isn't it? So what's our electrophile? NO2, the nitronium. All right, so they're showing you if you have the ortho, and if R is just a methyl group, you get ortho at 40%. If R is an isopropyl, so if that's your group, it's only 12%. Let's look for meta. We know that your R group for meta is going to be really low yield, right? So for meta, you get 3% and 3%. So that's basically nothing. You get a 3% reaction, folks. That's like, it didn't work. Here's your nitronium on the para. And here, if you just have a methyl, it's about 57%. It's still the major product. If it's isopropyl, it's going to be 85%. So consider the nitration of the alkyl benzene in Model 4. When R is an alkyl group, what nitration products would be formed preferentially? So alkyl groups are electron donating groups, so they're activators. So they're going to react faster than benzene, and they're going to be ortho para directors. And Model 4, compare the difference in the product distribution when R is a methyl versus isopropyl. Well, your para product is going to be higher yielding, and it's because it's bulky. Okay, the R group is bulkier for an isopropyl. Explain why there is a strong preference for the para product when isopropyl rather than methyl, and it's because of steric hindrance. So you're going to have more para because para is going to be further away from that R group. Looking at your problems, you have additional problems, and it says to draw the major organic products in each of the following reactions. So I need you to do that. And then it says on 15, draw the mechanism for each of the above reactions. So that means you're going to have to draw your major products, and then you're going to have to show your mechanism. So I want to see sigma complexes, reatomization. I want to see resonance structures for at least one ortho para director and for one meta director. If you want to show all resonance structures for all of them, for A, B, C, and D, you can, but as long as I see all your resonance structures for two of them, and they have to be, one has to be an ortho para director and the other one has to be a meta, then that will take care of that exercise.